So here we are, homework number 7, problem 1. And let's read the problem first. That's always a good place to start. Okay, so we have this conical dish that's got a slope angle right there, 30 degrees, and it spins, and we want to figure out the range of speeds that it'll go for this little block to stay at r equals 0.2 meters, and the block has a mass of 0.25 kilograms. And the coefficient of static friction is 0.3. Now that doesn't mean it's stationary; it's spinning around, but it's it's a static friction that makes it so that it doesn't slide up and down, right? So you could picture the problem. If it goes too slow, this block is going to slow down. It's going to start to slide down. If it goes too fast, the block is going to flip and go out that way. So we want to find a range. All right, so I've written out the problem this way, and I have a couple of cheat notes in case, so I can just see if I get the right answer. And okay, so the first thing we want to do is the all-important free body diagram. Let's start with the case where this block is going to go too slow and it's going to slide down. So we're going to write out the FBD and the IBD of this little block. And I think it's going to make it easier for us to draw the coordinate axis aligned. I like to call that x prime and this y prime right there. Anytime there's a slope of the thing. I think that will be fine for us right now. It depends. There's actually a little bit of a strategy here, and maybe I'm kind of like rethinking this. Maybe I want to have, because this is a normal and tangential problem, right? So maybe I want to write out the normal and tangential coordinate axis, maybe just to kind of emphasize that. Okay, so it'll be a little bit more complicated because of that, but not much. All right, so if we're going to use unit vectors, which is sometimes I do, I'm going to call that J, because sometimes people call that K actually. Anyway, this is EN right there. That's the important one. It's the unit vector, the normal, is going straight here. Tangential is coming in or out of the page. So I guess it's actually going into the page, right? Because it's rotating that way. So it's moving in that direction, right there. So that's the tangential, but the normal is perpendicular and it's towards the center. All right, so I'm going to try to draw the same block over here. You can tell that I haven't actually solved this problem before. So this is me solving it live. So there's always some chance that I'm going to screw some stuff up. But let's put all the forces that are going to happen onto this thing. And so we have a force downwards of the weight of the thing. So this is going to be mg. Sometimes I'll put it there W. If it was a US units thing, we're given the weight, and I'll just put a W there. But if it's SI units, I'll just put mg, just to remind myself. Now there's going to be a normal force, right, acting in that direction. So I'm going to go Fn right there. And we're going to have a friction force. Is there any other forces? I'm looking at this. No, okay. So this is going to be a case where it's going to go too slow. So I'm going to go case 1, too slow. Or almost too slow, right? So here is the friction right there. And we'll go F, because it wants to slide down, so better go that direction. And if we want to try to get like the angles, let's see, we'll put the angle in there. This is going to be the angle, it's going to be theta right in here. All right, and for the acceleration here, well, the only acceleration that's going to be taking place is towards the center. Now we say, well, is it going to move towards the center? No, it's not moving towards the center in this view, but if we had a top-down view instead, here's where the block would be, right? So we're tracing out the path of the block, and right there would be its tangential, and right here would be its normal. But we're just looking from this direction at the thing in this view right there. So it is a tangential and normal coordinates, but the acceleration is coming this way because we also know that the velocity of the block is going in that direction right there. So we have this setup. It really is a lot easier to have the axes going in this right here, but let me put right out there, continue. This is the mass times the acceleration in the normal direction. Okay, so let's write it in the j direction. Let's start out with the sum of the forces equals mass times acceleration. Maybe I should have called this, we know that it's y, so you go y right here, y. We know it's not going to accelerate in that direction, so that's kind of going to be helpful to us, I suppose, for what our intentions are. So that's the direction that we're calling positive right there. So we know that it's not going to accelerate here, so let's cancel that out and call it 0. And so some of the things I have to deal with here, let's see, we'll have to deal with this guy being theta, and I just don't want to make it too cluttered over here, but I'll try to write this out as being, maybe I'll move this label, and I'm just trying to figure out how I was going to put this in here so it's easier to see, so it's easy enough to see. Like I can maybe extend this a little bit. Put the theta right in there, right? So you can see that's where that angle is going to be, and here's my label for the friction force. I think you can understand that, right? Something like that. So anyway, in the vertical direction, it's the entirety of mg, and then in the let's see. Okay, so we're going to have the normal be right here, and that's going to be positive. And so we have Fn, but only the cosine of theta. And this is also, okay, so we have plus F right there. And that's going to be the sine, sine of theta. Something we also might want to know is that Ff is equal to mu s Fn. At this condition, right? So this is just on the verge of sliding downwards, right? That's what we always do for the static coefficient. And I think I got all the force over here. That equals 0. So we could do a little bit here. We can replace this FF, and we can put in some values. So let's go ahead and do that. And I think I'm going to be okay here. Yeah. So I got a mass time. So I got negative mg, so I got 0.25 right here, and let me tell you something you know, by putting in this value right here, it's going to work out, but it's also not going to show you something I know to be true, and it's going to, if we worked it out with algebra, we would find it's actually the mass doesn't matter, right? So in a problem like this, we would see that mass would cancel out. So I might want to keep this, I might want to keep the mass in there just to demonstrate this. I could put a value in there, but I'm going to leave it as a variable just to demonstrate that it will cancel out. Okay, so you got plus Fn times the cosine of 30 degrees plus mu times Fn, or 0.3 times Fn, times the sine of 30 degrees equals 0. Okay, so we can solve for Fn in terms of mass. So let's do that. So that m and 9.81 is going to go into the other side. I'll just do this right here, 9.8. I'll write it out, 9.81 right there, and m goes onto the other side. And we're going to divide out by the cosine of 30 plus 0.30 sine of 30. So we're going to get something multiplied by mass. So let's go ahead and work that out. 9.81, and to take 30 cosine and take 30 sine, but multiply that by 0.3, and then add it, boom, and then divide it, boom. And so we get 9.655 m. Now we could have gotten the actual value for the thing, and that might have helped us. But I think this is just demonstrating this kind of thing that comes up a lot, where we'll see it's a little counterintuitive. Sometimes if the mass doesn't matter, we think we're like, the larger the mass, the more it would maybe stick to the surface or something. Well, we'll see that it doesn't matter. All right, so we did that in the x direction. Now let's take the sum of the forces in the normal direction. It's going to be mass times acceleration in the normal direction. And that normal direction is defined to the left right here by our coordinate axis. So taking a look here, none of this comes into play, but some of this FF is going to come in, right, and some of this FN. So the FN right here, we'll write it in there and then we'll replace it, is going to be in the positive direction, right, and it's going to be the sine of theta. And then we're going to have a negative FF, and that's going to be cosine, because negative because it's going in that direction, but we divided positive was that way. Cosine of theta, right? And any other forces? No. And it's going to be equal to our mass times our acceleration right here. Now, that acceleration is going to be, this might be a little confusing right here. I think we're okay. This velocity that we have right here is going to be equal to r times omega. All right, so that this is ready, right? So here's the radius to the thing, and omega is coming this way right here. So if you just multiply this radius by this omega, you will get that velocity, because we want things in terms of omega. Therefore, we're going to say that the normal acceleration is velocity squared over, a lot of times we'll write rho, but we know that's the same as the radius. So what we did right here is we said that there'll be r squared omega squared over r. So another thing that we can write, if we want to write, instead of having v squared over r, we can always write r omega squared. Now you remember for polar, that was the same thing as r times theta dot squared, right? It's the exact same thing. This is centrifugal acceleration. So we can place that into here, right here, because we want to get things in terms of omega. So I can replace this thing right here. So I'll go 9.655 times m times the sine of 30 degrees minus, now remember this needs to be, we can write mu s times fn, so 0.3 times fn, 9.655 m times the cosine of 30 degrees. Oops, that went down too far. Okay. And then equals m times my, well, I'll write the an right there so you can see that. So we have r, which is 0.2, and omega squared, and that's the thing we want to try to find, right? We're going to try to find what this value is when this thing is going to balance out. Notice though, m, and m, they all cancel out. It didn't matter how much mass. Wouldn't control whether this thing flies out or actually slides down. But this is going to be the slower of the two right there. So let's see. We'll plug all these numbers in. 9.655 times the sine of 30. Okay. And then 9.655 times 0.3 times the cosine of 30. Boom. And we subtract that in this case. Bang, bang, boom. And then we're going to divide by 0.2. And then we're going to take the square root of it. Boom. And so we find that omega is 3.405. And these are radians per second. And I just want to take a little peeky poo. Peeky poo? Did he really just say that? I think he did. Oh, yep, I got the right number. Whee! Yay for me. All right, now we have to do the whole thing over again. Nah, it's not that long of a thing. Now we want to do the other one, case 2. We could have been, so this is like too fast. And maybe I want to make this a 1. Let me put a 1 in here all over the place. I guess this is still general right there, right? 1. But this is the case where we went too slow. Now we're going to go too fast. I need another FBD. Don't be lazy. Just try it again. It didn't take that much time. We'll catch up on that time that's going to be used at some point in our lives. I went J there. We'll go IBD. And just think of it as practice. Practice? You don't need practice. Yeah, we need practice. We definitely need practice. And just draw the boxes. I don't want to draw the boxes. No, draw the boxes. Let me see. And almost everything is going to be the same except for the friction. Right, so we're going to have the same weight coming down here, mg, and in a normal force, but this normal force is not going to be the same. And now, let's see, we're at Fn. Now the friction force goes this way, right? Because it's trying to slide that way up here, and we don't want it to. The acceleration is still towards the center. That hasn't changed. Right there, so this is going to be m times an, and this is ff, and let's see if we can get this angle right in there, is theta, and now the angle here is still going to be theta, there. Right. And so we get the sum of the forces in the y direction equals mass times acceleration in the y direction. We know it's not moving in that direction, so we can go ahead and put there. So we work through this thing, and we're going to find that one of the SIGN signs flips, right? So it's basically the same thing. We still have negative mg. We still have a positive Fn cosine of theta, but now we're going to have a negative, because he's going downwards, negative ff sine of theta equal to 0. So just as before, I'll keep the 9.81, negative m 9.81 plus my Fn cosine 30 degrees minus 0.3 times Fn, right? I substituted that mu s into there. This is the sine of 30 degrees equal to 0. So I can find an Fn is going to be, let's see, we're going to take 9.81, right, and we're going to divide it by the cosine of 30, and take the sine of 30, but multiply it by 0.3, and now this time subtract it out, right? It wasn't before. And now we're going to take 9.81 and divide it by that value. Boom. And we end up getting 13.70 times m. Great. So that, and before, what did we get? We got 9.655. Now we get 13.7. That's the real difference. And then we'll take the sum of the forces in the normal direction equals mass times acceleration in the normal direction. Once again, that's positive. And okay, we're going to have now we're going to have a positive ff because he's going in that direction, right? Whereas we didn't before, right? We have Fn is also, well, I'll write Fn first. Let me write Fn again first, just to be similar to that right there. We have Fn, and that's still times the sine of theta, but now we're going to have a plus ff times the cosine of theta, right? As before we had it as minus, right? Let's really the big difference. And that's all we have, and then we're going to have mass times acceleration in the normal direction, which we could, well, we'll do it down here. So we'll have, we'll place this, 13.70 m sine of 30 degrees plus 0.3 times m cosine. Oops, sorry. Right, so I replace that FF with a 0.3 times, I needed that, whoops, there you go, 13.70 m cosine of 30 degrees. And did I do that right? I think so. And then I have m times, remember we want to go r omega. So 0.2 is r, and this is omega. We'll call it omega 2 squared. From this, we can find omega 2, noting that m cancels out everywhere. So let's do it. We have 13.7 times the sine of 30. Boom. And then we have 13.7 times 0.3 times the cosine of 30. And now this time we add them together, and then we divide by 0.2, and then we take the square root. And we end up getting 7.214 radians per second. And that matches up with the other solution to this, yes. So I got just enough room to write answers. So I'll write, we could write it out this way. 3.41 radians per second, omega 7.21 radians per second. That expresses correctly, right? So this is the range. And this problem I took directly from Miriam and Craig. My dynamics book from 1988, 1989. Let's see, I was the class of 1992. KP, USMMA, KP 92. Out of the zoo in 92. And I had Don Paquette as my professor. And he said he was going to write a textbook, but then he ran across this textbook and he said that he couldn't do a better job. In 1986, right? It was the second edition, right there, second edition, Miriam and Craig. Oh, here we go. Good problem. So we'll get rid of the video. 23 minutes. That's a long video.